Hi everybody, this is the video going over the lab number 5 for one-way ANOVA. As noted on the lab document, make sure that you watch this video before you actually do the problem. And so it's similar to the last labs that we've done, in that you'll be outlining the steps in SPSS and you'll be interpreting some data. So first, let me just show you how it's generally done. I'm going to be bringing up a data set. So this is just a demonstration. This is not what you're going to be doing for your lab, but this is a demonstration of what it looks like. And so how you run an ANOVA is analyze, compare means, and there's a one-way ANOVA here. And I'm going to just reset this because I had something run before. And in these data, we have voting behavior from way back when, I think it's 1992, in the presidential election, and we have a bunch of other data. So what we're going to do is we're going to look at categories of who people voted for. In that year, there were 3 major candidates. There was Bill Clinton and the father, H.W. Bush, George H.W. Bush, and Ross Perot. And so there was basically 3 major candidates that people are voting for. So this is a categorical variable because we can't say that Clinton is half of Bush and Bush is twice as much as Perot, or it has no interval level, or not even ratio. That's a ratio. But we can't even say more or less. We can't say voting for Clinton is more than Bush. That doesn't make any sense. They're just different categories of people. So this is a category, and we have 3 categories again: people who vote for Bill Clinton, people who vote for the father, H.W. Bush, and people who voted for Ross Perot. And so we put this, and these are real data, by the way. These are real data collected by University of Michigan. So that goes into our factor. So the thing that we have groups, and again, this is groups of people in terms of who they voted for, whether it was Bill Clinton, H.W. Bush, or Ross Perot. So those are groups, categorical data, nominal data. So it goes here in factor. So your independent variable, or I shouldn't say independent variable per se, but your variable that is categorical. So in most cases, we have experiments with independent variables, and there would be 3 groups or more, that would go here. But just any nominal variable that has 3 or more categories, we put there. So dependent is what we're relating it to. And so the question I'm going to ask is there an age difference in those groups? Clinton voters versus Bush voters versus Perot voters. So is there an age difference? So the dependent variable in one-way ANOVA approximates at least interval level of measurement. In this case, we have a ratio level of measurement, which is age. So we put the at least interval, approximating interval, dependent variable in the dependent list. We put in factor, we put the groups. Unlike the t-test, we don't have to define the groups. The computer already knows that there's multiple groups, so we'll just look at them. And then there's 2 things we need to do before we run it. One is we need post-hocs. So remember, post-hocs are done if we have a significant F. So the F will just tell us whether there's a difference in age between those 3 groups, but we don't know where those differences are. So the post-hocs figure that out. So you can see here that there's at least 14 major ways of doing post-hocs. So again, you don't have to do these by hand. And what post-hocs just simply do is they just basically split up the probability of making a type 1 error among all the comparisons it needs to do. Tukey is a nice, safe, conservative thing to choose. So I'm going to choose under post-hocs Tukey. And all I just say is continue. And you can see there, right here, the default is an alpha of 0.05, a 5% chance of making a type 1 error. We'll just leave that. That's what we've been using. Press continue. Then we go to options, just a little tricky thing in ANOVA. I don't know why they don't do this automatically, but let's check descriptive so we can look at our group means and standard deviations so it's easier to see what's going on. We also need this for our table of descriptives. And so in the lab, you're going to be asked to write a result sentence and to have the tables that we had in our homework, which are the descriptive tables and then the, excuse me, the ANOVA summary table. So you need to write those two things up, and we need the descriptives to do that, obviously. And so those are the steps I'm outlining. So I'm outlining number 1 for you here. So just say continue for descriptives, and we just press OK. And I'm going to snip this, just like in your output for your actual lab. I'll have to snip this in 2 parts because I can't get all of the relevant output into one screen here. So I'm going to snip it into 2 parts. So I'm going to snip the first part of the ANOVA findings right here. And I'm going to magnify it a little bit. And I'm going to write on it. So this is the first part of the ANOVA output from SPSS. And so for your 2 questions, this will be the first part of that. So it'll be part 1 and part 3 will give you this first half for the 2 questions that I'm asking on the lab. And so it's very much like the T output in many ways, but let me highlight. And there is like 4 people, there are 4 people who vote for other. I'm just ignoring that. So we're going to consider this to be 3 groups. So this is whether they voted for Bill Clinton or H.W. Bush or Ross Perot. So there's 3 groups. That's where your groups are. Just like your t-test, except in the t-test it has 2 groups there. And so it tells us what our sample size is for each group. We don't have to worry about that so much. Let's look at the mean. What's that a mean of? Well, remember, it's our dependent variable. Well, if we ever forget what our dependent variable is, it's just right there. It's the age of the person telling us who they voted for. So we can look at this and see the means. And actually, before looking at our F, you can kind of look here. You can see that there might be some difference. I'm just looking eyeball, and it looks like the Perot voters are a little bit younger than the Clinton and Bush voters, just looking at this, eyeballing it. It's not a significance test, but just kind of getting a sense of the data. It looks like there might be a difference there. And then we have our standard deviations for the 3 groups. And so when you do your table number 1, here's your stuff. So table 1 is descriptive. So for Clinton, here's the mean standard deviation. For Bush, mean standard deviation. Perot, mean standard deviation. So just write the table just like you did for your homework. The data are right there. We don't need to worry about confidence intervals in this case. We'll just ignore that. And then we'll jump down here to the ANOVA stuff. So here's the ANOVA. This stuff should look really familiar. This is a summary table. This is an ANOVA summary table. And it looks just like the ANOVA summary table you did in your homework. So we have between groups variance, we have within groups variance, and then we have total. We have the sum of squares here. So sum of squares between, within, total. Remember that we round up to the 2nd decimal place when we're reporting data in APA format. We have the degrees of freedom right here. So degrees of freedom between, within, total. Keep it as 3, even though I told you to ignore this. It's the mean for 4 people. This is just a demonstration. Just keep it as is if you were going to write that up. And then here's our mean squares. Just like in our summary table we did for our homework, which is the sum of squares between divided by degrees of freedom between equals this. Then we have our F, which is mean square for between divided by mean squares within. So df is there. df is 6.24, again, round to the second decimal place. And here's our significance level. So you see it doesn't say two-tailed here, so this is a one-tailed significance level. We don't need to worry about it. Why is it one-tailed now? Because there's no direction in ANOVA prediction, correct? Because we're not saying one group's greater than another group. The hypothesis we're testing is just simply, are there differences among the groups? We don't know where the difference is. It's just there's some difference there. So there's no direction to the hypothesis. So they're giving us a two-tailed significance level. I'm sorry, one-tailed significance level here, which is nice to have. I'm not sure why we can't ask for that in a t-test, but that's the way life goes. It's not perfect. So in this case, we don't need to do any division by 2 or anything like that. We can just keep this as the significance level. So let's look at the significance level. I'm going to ask you, is this significant? Significant means we are going to reject the HO. Significance means that there is an effect there. So are we going to reject the HO here? I'm pausing. You can actually pause the video if you want to think about it. Yes, we are. The significance level is 0.000. And so if something is less, if that sig is less than 0.05, we reject the HO. So if we reject, again, don't make fun of me in terms of my writing. I have a very small little laptop thing, and I have to do it on the pad here, all this writing. So the sig is less than 0.05, we reject the HO. Again, the significance here, what's going on here is that the computer is giving us a very specific a very specific type 1 error probability. So it's telling us that we're essentially at 0. You can't be at 0, so it's probably like a 0.001% chance that we make a type 1 error. So it's a very small chance that we'd make a type 1 error, so it's less than 0.05, less than a 5% chance of a type 1 error. So we're going to reject the HO, and the HO in this case is that the groups are equal. So when we reject the HO here, we're just saying that the groups are not equal. We don't know which ones differ, it's just that there's some difference there. We have to explore that with post hocs, remember. So remember that the ANOVA is a protected test, and we have 2 stages. The first stage is looking at the F, and is it significant? If it is significant, then we have to look at the post hocs to see where the differences are. And we'll get to that in a bit because that's in the second half of the output that I'm going to show you. So here in terms of your write-up, again, you have your table 1 here, the groups, mean, standard deviations. Here is your ANOVA summary table. You really just have to type these numbers in. This is already exactly what you need for your ANOVA summary table. And then right now, I'm going to tell you the first few sentences that you'll be writing. Of course, it'll be just like your homework, so there'll be a sentence saying something like see table 1 for the means and standard deviations for the groups. See table 2 for the ANOVA summary table. That's all you need to say for those 2 sentences. And then for sentence number 3, we have to give the overall finding. And so here, we would say that age is significantly related to who people voted for in the 1992 presidential election, comma, F, parentheses, 3, comma, 1002. That's our degrees of freedom, with 3 coming first and then 1002 coming next. So the between comes first, the top part of the ratio, between, within, and then the bottom part, within. So F, parentheses, 3, comma, 1002, end of parentheses, equals 6.24, comma, P is less than 0.05. So that's our overall sentence, very simply. You might ask, well, why don't we have the means and standard deviations in the sentence? It's very confusing for one, so it's not like a t-test that just has two groups, so we don't want to cram in a bunch of information, so we just have the table. That's why we have table one. We can just put table one here, and people can look real easy and see what the means and standard deviations are. If we put 3 means and standard deviations in a sentence, it gets really hard for people to see. And also the sentence gets too long to really have it be short and sweet, which is scientific writing is short and sweet. So that's the sentence. You can replay the video if you want the sentence again. And again, all that information is gotten from here. And you have table 1 stuff here, you have table 2 stuff, you have that sentence. So now we have the overall interpretation that there is some difference between the groups, but we don't know exactly what they are, although we've looked here at the means and we've gotten a little bit of a sense. It looks like Perot's lower, but we haven't tested that yet analytically with our statistics, so let's do that. So again, I have to break it up into 2 parts, just like your lab output in Canvas. I need to break it up in 2 parts because I can't fit everything in 1 page. So let me snip this so it's easier to see. So snipping it. And so this is our post hocs. So remember, we only look at our post hocs if our F is significant, because it's a protected test. If it's significant, then we can start looking at the pieces and see what's going on. If it's not significant, we can't go dig into the pieces because we are going to violate our alpha. We're going to make a larger than 5% type 1 error. So that's just the rules of the game. So the F protects us against having an alpha greater than 5. And once the F is significant, we can dig into the pieces. And so here is the post hocs. I have to double check that I clicked this. I don't know if I did. So here's our post hocs. This will be part 2 and part 4 in your Canvas materials. So part 2 is for question number 2, part 4 is for question number 3. And so it just tells us it's Tukey. HSD means honest, significant difference. Don't ask me why they say honest. I don't know if there's a dishonest one. It's just people like to play with things sometimes in terms of names. And so we have to be very careful here. For one, I said that there's only 4 people here in the other, so we're just going to ignore this thing here, and we're going to ignore anything that says other. Don't worry, for your labs, there's cleaner data than this. Just frankly, this is the only data that I had that I could show you some demonstration about what things are going to happen. So know that things are repeated. So there's actually 3 comparisons. There's Clinton versus Bush versus Perot. And then there's Bush versus Perot. There's 3 comparisons. But here we have 6. Why do we have 6? It just repeats the same thing. So here we have Clinton and Bush, but it's repeated here. And you notice the numbers are the same. So I'm going to cross this out. This is a repeat. This is a repeat. You see it's the same number as this right here. And then I'm going to just cross this off also. And then this other thing we're ignoring. And then this is a repeat too. So we already have Clinton and Perot. So it says Perot Clinton. It's the same thing. You can see it's 4.915. It's the same thing except it's the negative just because you flip how you're subtracting the ages for the groups. So that's a repeat. So we don't need to look at that. And same thing here. So here's Bush and Perot. Perot Bush. I don't know why I said Bush like that. That was just because I said Perot. And so it's the same. It's 5.67. It's the same number. So we just ignore these things. There's a repeat on these things. So essentially, we're only looking at basically half the output because all of this other stuff is repeats. So we just have to be careful with that. So when we do correlations later on, it's the same problem. It just gives you the numbers twice. So we just have to remember we have to play the game along with that machine and not to get too confused with things. So we really have just three numbers. We just have Clinton versus Bush, Clinton versus Perot, and Bush versus Perot. There's three groups. Those are all the comparisons that we need to make. And for your labs, I'm only going to give you three groups. So you're only going to be looking at three numbers. So the big trick also, so we've crossed out this. Sorry if it looks a little bit messy. I just want to highlight that we are not looking down here. We don't need to. All our information is up in these three lines. This line, and this line. We don't need to look at anything else. And you can ignore the mean differences. All that is taking the differences between the two means. We can look at the table if we want for that. We can ignore this. We can ignore the confidence interval. We don't need to worry about that for our ANOVAs. The only thing that we really need to look for is sig, significance. Remember that sig is significance. What the computer is doing is it's actually giving us a specific type 1 error. And we go back to the first part of the lab output to sort of reinforce some of that. I was going to do that, and my mind slipped slightly. And so what we're going to be looking for here is we're looking for sigs that are less than 0.05. Why? Because in these comparisons, and these are essentially like t-tests, we're just running multiple t-tests here, but we're protecting ourselves with a Tukey from making a type 1 error. We're essentially dividing the 0.05 into three parts there. But again, we're looking for this. This is the magic number. For every single SPSS output we're going to be looking at for inferential statistics, this is the magic number. This is what we're looking for. So this one, no good. Not less than 0.05. This is good. Less than 0.05, not good. Anyway, it's another. And then this one. So we have two sigs that are less than 0.05. So that's telling us there's a difference between the two groups. So what are the differences? So this line here is Perot versus Clinton. So the voters who voted for Clinton versus Perot are different in age. And I'm going to look at the output later, the descriptives that we looked at before, to see which is which. So remember that Clinton is different from Perot. That's what that's saying. This one, the second one, that's less than 0.05. We look at this and there's Perot again and Bush. So Perot is different from Bush. So Perot is different from Clinton. Perot is different from Bush. So we have to go look what's going on. And by the way, Clinton and Bush, they don't differ. So Clinton-Bush, which was this line, they don't differ. There's no difference. It's not less than 0.05. So hopefully that's not too messy of a markup. I just want you to know what not to look at and what to look at. And essentially it's just these two things and knowing that these things are repeated. Okay, so let's go back to our output before, and I'm going to make a snip here. So again, from those post-hocs, we know that Perot differs from Clinton and Bush, and Clinton and Bush don't differ. When we looked at that comparison, they didn't differ. So Perot is different from Bush and Clinton, and Bush and Clinton do not differ from each other. So this will make a lot of sense when we go look at our, give me a second here, sorry about that. I need to go up the output here. And so whenever you're looking at those things like t-test or ANOVAs and you're confused which one is higher and which one's lower, don't worry. Some people asked me or emailed me and said, what's the hypothesis? I don't know what to say, which one's different. You don't need to know. A hypothesis is needed, of course, for doing research, but for statistics, we could actually just look at this stuff. So again, we know that Perot, let me make sure it's marking. We know that Perot is different than the other two. Again, we're going to ignore the other. So Perot is different from Clinton, and Perot is different from Bush. And those two people, Clinton and Bush, those voters do not differ in terms of age. And that makes sense here. Look at this. So the average Perot voter is 43.42 years old. And the average Clinton voter is 48.33, and the average Bush voter is 49.09. So looking at these numbers, we know that Perot voters are younger than Clinton and Bush voters. And so here's where we can actually report these things. We don't have to put it into the sentence because we have the numbers in our descriptives. And I'm seeing a rainbow, at least one end of the rainbow. That's kind of nice. And so our sentence would be simply something like this. So after we reported our overall findings with our F, which I stated that sentence earlier in this video, we would simply say, post hocs suggest that Perot voters are younger than Clinton and Bush voters. And that would be fine for this class. So again, post hoc, you can say post hocs or post hoc test, doesn't matter, either one. Post hocs suggests that Perot voters are younger than Clinton and Bush voters. And the rainbow is getting bigger, so excuse me for sort of leaning around and looking at that a little bit more. So that's a simple sentence. And you can see, if you just look at it, you can kind of see that already. You can kind of see that relationship. And that's all you need. All you need is a sentence for table 1, descriptives, a sentence for table 2, summary table, a sentence giving your overall finding that age did relate to who somebody voted for in the 1992 presidential election. You give the F information in that sentence, like I did before. And then you have a sentence about the post hocs if you have a significant F. So post hocs suggests that Perot voters are younger than Clinton and Bush voters. And again, you don't need to put the means and standard deviations in that sentence because you already have this table. If somebody wants to see the ages, they can go and look at this table. And that's basically it. So when you are interpreting the output, that's how you do it. And so now I'm going to show you the two pieces of data. I shouldn't say pieces of data. Two data sets that you're going to be looking at to interpret your output for labs, for your lab. So let me close this. And I want to make sure I have everything here. So question number 2, and I want to double check this. So question number 2, you are going to be looking at data from students at the Claremont colleges who took a stats class 1 year, and we're going to ask whether age relates to sleep. And so sleep is the dependent variable. That's the thing that is, in this case, it's a ratio level variable. It could be approximately interval, but in this case, we know it's ratio. And age, I made into groups. And so when you interpret the output, remember this code. So in the output, for group number one is 18 and 19-year-olds. Group number 2 is 20-year-olds. And group number 3 are 21 plus people. And so go ahead, remember those groups. And I ran this for you. And I want to check that Canvas is still working. Sometimes Canvas logs you out if it's if it thinks you're sleeping on it. So I'm just going to click that real quickly. And so what I did is I took that class survey data, and again, it's analyze, compare means. One-way ANOVA. I'm going to reset this. And so the age category is down here. So remember, this is not age as a ratio variable. This is age in terms of groups. So the three groups again are 1, 18 to 19-year-olds, 2 is 20-year-olds, and 3 is 21 and above. So I put age into groups in this case. So that's why it goes into the factor thing, that goes into the groups. And then we're curious if these groups, these age groups, if they had different hours of sleep. And so how many hours did you sleep last night? That goes into the dependent variable. Remember that we have to tell it to do a post hoc, just in case it is significant. Press continue. Options. We want the descriptives because those means, especially, we want the standard deviations too for our output, but we need the means to sort of interpret which groups are different if we get a significant overall F. So we press that, and here's our output. So the output looks just like the output I showed you. Just remember that I'm going to snip this real quickly. Actually, I think I thought I had that done my thing. I have to remember it's there. So like, if you double click it, it really messes you up. I'm going to pin this. I thought I pinned this before. It's a bit annoying. Oh, it says, oh, pin from the start. I don't really see it on my start, do I? Sorry about this. I wonder if I can pin it down here. If I move it, it refuses to. Stupid thing. So let's just redo that. And I'm just doing this to remind you about what's here. So again, this is listed in your lab. So just to highlight. So it always gives the DV here. So the DV is that at least approximate interval. In this case, it's a ratio. And then we have the three groups here. So they're not labeled, but remember I gave you this information in the lab. So group number 1, 18, 19-year-olds. Group number 2 are 20-year-olds, and 3 is 21 and above. That's what these groups are. And remember that the means here and standard deviations here. So that's all I'll say about that output. I will highlight in Canvas the output for this, and I also state this in the lab, is for question number 2, you want part 1 and part 2. Part 1 is the descriptives and the F information for that question. Part 2 is the post hocs if you need it. So that's one part of the lab. I'm going to close this. By the time I'm with this video, I'm going to close SPSS for a few days. And so the second question, I should say second question, it's officially the third question, but the second thing that you're going to be doing in terms of looking at output is, again, there was actually some data that was collected from a stats class at the Claremont Colleges even before I was working there. So a stat professor collected these data. And I don't know how he measured the various things, but basically he measured people's levels of extroversion. And he categorized people as extroverts or introverts or in between. So there's three groups again: extrovert, introvert, and people who are in the middle, in between those two extremes. And so that's your group variable. That's your predictor variable here. That's categorical. And then The DV is the number of best friends that you have. So this is how I ran the data. So compare means, again, analyze compare means. One-way ANOVA. I'm going to reset this whole thing. This extrovert thing without an E. Whoops. Looking at the rainbow still, it's getting big and bright. Is the groups. Remember, that's whether you're extroverted, introverted, or in between. So there's 3 groups there. And then number of very close or best friends. So that's actually ratio. Again, it only needs to approximate interval, but in this case, we have a ratio. Measured variable. We need to do a post hoc just in case it's significant in terms of the F. So press 2 key is a good choice. And it's again, it's 0.05 for the alpha. We don't have to worry about that. That's the one that we always use, and that's actually the default in SPSS. Options, we want to see the means. Standard deviations are good also for our table 1, but the means tells us if there's any difference, which group is larger or smaller than the other groups. And so run it, press OK, and then here's the output. And let me I'm still obsessed whether I can pin this. I don't know why I can't pin it to my taskbar there. That's dumb. So anyway, just to show you the first part of the output. Actually, I'll show you both in this case, just because it's easy to do. So this output is in Canvas. And so I'll show you real quickly. So part 3 of the output on Canvas is for this problem, and it's the descriptive statistics, as well as the F table that we'll see in a second. And then part 4 is for that same problem, but it's the post hocs. So I wish I could do everything in one picture, but it doesn't fit in one picture, so I need to break it up. And so I'm just going to highlight real quickly here. Same thing, we have the descriptives, we have the mean, we have the standard deviation. In this case, we have the label of the group. So we have people who are really extroverted, people who are really introverted, and people who are in the middle. And then we have their mean, standard deviation on what? Well, on the dependent variable of how many very close or best friends they have. And then just as a reminder, this is the ANOVA summary table. And so you'll be looking at the output. And then if this F is significant overall, then you're going to be using the post hocs, which are in part 4 of the output on Canvas. It's right there. And I think that's it. I don't think I need to run over anything else for this lab. So hopefully that was useful. And you will have a lab for this one-way ANOVA. We are not going to have a lab for repeated samples ANOVA. Why? I don't think I still have it. You can take this as some sort of empirical proof. So analyze, compare means, look here. You don't see repeated samples ANOVA here. You have your t-test, and then you have your one-way ANOVA. For whatever reason, SPSS, IBM, probably because not many people use it, because they're starting to sell it to businesses. And so business people usually don't know what the heck they're doing with stats. That's why I was telling you, if you can understand stats, then you can really leverage that into well-paying jobs if you're ambitious about that. And you don't have to do stats all the time. Just the ability to do that and have that in your pocket is useful. And so the bottom line here is that repeated samples, ANOVAs in SPSS, they're really clunky. You really have to do a weird thing with them, and the output is yucky. So the bottom line is I'm not requiring you to do a lab for repeated samples because of those very reasons. So you only have one lab for the ANOVA stuff, and that's this lab with the one-way ANOVA. And we can say goodbye to SPSS. and you can say goodbye to this video lecture. So it's not a lecture, a video lab help. So hopefully this was useful, and let me know in the live sessions if you have any questions. Or you can email me also, but the live sessions are also good because I can demonstrate things that go on. Okay, take care. Hope everything's going well with everybody, at least as well as it can under certain circumstances we have right now. So take care, and I'll talk to you later.